So welcome back, children. In the previous videos we talked about the lens maker's formula and how the light rays are refracted through a lens, and we also talked about different types of lenses: biconvex, biconcave, plano-convex, plano-concave, and then convexo-concave lenses. Okay. Now we'll talk about the power of a lens. What do you call as the power of a lens? First, let me write the lens formula. This is different from the lens maker's formula. So the lens formula is this: 1 by V minus 1 by U is equal to 1 by F. This formula is true for all types of lenses. Even though we derived it for one particular type of lens, the biconvex lens, the double convex lens, this formula is applicable for all types of lenses. Okay? But if it is a convex lens, the F is a positive number. Okay? If it is a concave lens, F is a negative number. It's negative number. So for plano-convex, plano-concave, and then convexo-concave, whether it is a net positive or a net negative decides what type of lens it is. Okay, convexo-concave lens. Anyway, so now we are going to talk about the power of a lens. Right? So power of a lens. The power of a lens is defined as the ability of the lens to bend the incident ray. A ray falls on the lens and then the lens bends it. How much can it bend? The more it bends, then the more powerful it is. If it bends only slightly, then it is less powerful. So the lens, the power of a lens depends on its ability to bend the incident ray. Okay, let's put it that way. Then there are different types of incident rays, and how do we define it more perfectly? For example, if we take this lens, there is a ray that can fall like that, and there is a ray that can fall like this, there is a ray that can fall like this, and there is a ray that goes like this, and then there is a ray like this, and there is a ray which is parallel to it. There are many different rays, and all of them will be bent differently. Right? For example, if we take this ray which goes through the optical center, this will not be bent at all. What will be the lens? This will not be bent at all, it will go straight. Right? And other rays, it can be bent differently. So then we need to look at. So I think there is an R here. Okay, the I is greater here in this case. So then R will also be greater, like this. You see, the bending is more in the case of this ray. So how do you choose which angle as a reference angle to even say this? Well, I can take, instead of all this, I can take a parallel rays, right? Okay, I'll say, well, I'll do it this way. Let me take parallel rays. And I can say that the power of a lens is the ability of the lens to bend a parallel ray, or the angle. So, if the lens is powerful, then it will take this parallel ray and it will bend it more. And that's a problem again. This also is a problematic. Why? Because all these rays which are parallel to this, parallel to the axis, will go through the focal point. You see, now it goes like this, and it goes like this. And if there is something else which is much bigger, wider than this, then that will go like that. You see, look at this. This angle is smaller, and this angle is bigger, and this angle is the biggest. So the farther the parallel ray is from the optical center, then the angle of its bending is more. So which one are you going to take? So the definition is this. I'm going to take the ray which is 1 meter high from the lens. Okay. And I'm going to see at what angle that particular ray is bent. And that angle is what I'll call as the power of the lens. So there are many different parallel rays parallel to the axis. And each ray will bend at different angles because all of them have to go through the focal point. So I have to take one particular ray, and this ray is about 1 meter from the axis. And I'll take that particular ray, and I see like how much this is bent, at what angle it makes now. And that I'll say as the power of the lens. Does it mean that every lens is at least 1 meter wide? No, it's not like that. When I do the calculation, you will understand that no lens will have to have that 1 meter width. It doesn't have to be 1 meter wide. Okay, so let's see this. Okay, so let's suppose that I have a lens like this. Okay, it's a really big lens. Okay, and then let me take this ray, and which is 1 meter. It's parallel to the axis at a distance of 1 meter from the axis. Now this ray, like any other parallel ray, will have to go through the focal length. So suppose this is the focal point. If this is a focal point, then this will go through that point. Okay. So I'll say this is the angle. Okay. So what I'm going to get now? So if it bends more, this angle will be greater. If it bends less, then this angle will be smaller. So this angle gives me a measure of how much this is bent. Right? If it is bent 90 degrees, and you just go through this. It doesn't happen, but I'm just saying. If it goes parallel, if it goes straight, then it's it doesn't bend at all. So it is 0. It goes straight. But the more it bends, the greater this angle is going to be. So now, what is tan theta? Tan theta is equal to this height divided by that distance. Okay, so I'll call this as O, this is as A. Okay, and I'll say that this is F. Okay. Tan theta is equal to OA divided by OF. Okay, so what is OA? OA is 1 meter, right? So it's 1 meter. What is OF? OF is going to be small f. That's the distance. OF. Tan theta is this. But I said theta. Theta is what I need, right? So tan theta is what I define. But notice here, if this lens is really big, okay, it's really big, and so that if this can be a paraxial line to this, if it is so big, then you see, then this distance can be neglected, right? If it is so big and the curvature is not that much, it doesn't curve too much. It slowly curves. Then, even at 1 meter, if we drop a vertical line from there, the distance between the line, the point at which it meets the axis, and the periphery of the peripheral point of the lens would not be much. You can ignore it. So that's what we keep saying about paraxial lines, right? So if this is really wide like this, then if I drop this vertically, and this I can ignore this distance. It will be really close to it. Right? So in that case, then my tan theta can become theta. Okay? So then theta, this becomes 1 by f, and this is what I call as the power. So power of a lens is defined as 1 by f. So even though we have done it for a really big lens, once you get this expression, this can be used for even a very small lens, because all you are concerned about now is the focal length. So it comes from here. So how much it bends? Yeah. It does this. So the power of a lens is defined as 1 by f. So what is the original definition? The power of a lens is the angle at which a parallel ray, which is at a distance of 1 meter from the axis, is bent. Okay, the parallel ray will go through the focal point. So the angle between the axis and the focal point is the angle at which it is bent. And if you talk about paraxial rays and stuff, then that tan theta will become theta 1 by f, and you can define it as power. So once you get to this point, P is equal to 1 by f, now you don't have to worry about 1 meter, 2 meters, 10 meters, you forget all of them. You can apply this to any lens of any size, even a a 2 millimeter lens, you can still be able to apply this. A 6 millimeter lens, you will still be able to apply very easily. So this is how the power of a lens is defined. So okay, we have defined the power of a lens like this. Power of a lens P is equal to 1 by f. Then what is the SI unit for the power of a lens? Well, you can do this. This is equal to 1 divided by this f. Right? F is going to be in meters. So that gives you the power of a lens. The SI unit for the power of a lens is diopters. Okay. So the SI unit for this is diopter. If the focal length is positive, then you will have positive power. If the focal length is negative, then you will have negative power. So when you go to your optometrist or an ophthalmologist doctor, and when he gives you a prescription, you say that when he checks your eyes and then gives you a prescription for your glasses. So you have minus power, which means that your focal length is negative, which means that the lens you have is actually a net concave lens. And for people who are over 40 and who are suffering from long distance vision, long sight, right? So when you suffer from long sight, then for them the power would be positive. So they would be using a net convex lens. Okay, so the unit is diopters. You say what is your power? 1.5 diopters, or minus 1.5 diopters. So that's how it is. Okay. Anyway, so with that we'll go do this problem, exercise problem, example problem 9.8. The first part is this. If the f is equal to 0.5 meters for a glass lens, what is the power of the lens? It's very simple. So the focal length is given. Focal length is, so this is 9.8. So first part, the focal length is given to be 0.5 meters. Okay. So they will ask you to find the power. So what's power from this expression? P is equal to 1 by f. F must be in meters. So 1 by 0.5 meters. So that gives you 2 diopters. So this is the power of that lens. And the second part is this. The radii of curvature of the faces of a double convex lens are 10 centimeter and 15 centimeters. Its focal length is 12 centimeters. Then what is the refractive index of the glass? So what have they given? So you have a second part, you have a double convex lens. So radius R1 is given, which is 10 centimeters, and then the other radius R2 is given, which is 12 centimeters. Okay, so one must be positive, the other must be negative. They just given you 10 centimeters and 12 centimeters. It depends on where you are going to keep the object. If you keep the object here, then R1 is going to be positive and R2 is going to be negative. Okay, and if you keep the object here, then this becomes R1 for me. Okay, then this will be plus 12 and then we get minus 10. Okay, so let's suppose I am going to keep the object here on this side. So this is my R1 and this is my R2. So this is my R1 and this is my R2. Okay. So this is positive and this will be negative. So this is the cable like that. And the focal length is also given. The focal length is 12 centimeters. F is given. F is 12 centimeters. Is this positive or negative? This has to be positive because you got by convex lens. So focal length must be positive. So this sign is fine. R1 I have taken to be 10, R2 I have taken to be minus 12 and F to be 12. Okay? Now they want you to find the refractive index of this glass. How do you calculate the refractive index? That's easy. What's the lens maker's formula? Which is 1 by V minus 1 by U is equal to N21 minus 1 into 1 by R1 minus 1 by R2. Okay. This is lens maker's formula. This is LMF. What is the lens formula? The lens formula is 1 by V minus 1 by U is equal to 1 by F. So from this I can say that N2 minus 1 minus 1 into 1 by R1 minus 1 by R2 is equal to 1 by F. So this is 1 and this is 2 and I can combine them, then I can get this. 1 by F is equal to N21 minus 1 into 1 by R1 minus 1 by R2. Simple. So I have all the information defined into it. It's very easy. So 1 by F is positive, so 1 by 12 is equal to N21 minus 1 I keep, and here 1 by R1. R1 is 1 by 10 and minus of 1 by minus 12. Okay. So that gives me N21 minus 1 into 1 by 10 plus 1 by 12. Okay. Then 60 could be the LCM for that. If you take 60, take 1 by 12 is equal to N21 minus 1 to 60. So I have 6 plus 5 by 60. So that is equal to 11 by 60 into N21 minus 1. Okay, so this will go and I will get 5 here. So if I bring it all to this side, I'll say N21 minus 1 is equal to 5 by 11. So N21 is equal to 5 by 11 minus 1, that gives me plus 1 gives me 11 plus 5, which is 16 by 11, so this is approximately equal to 1.5. Okay, so the refractive index N21 is equal to 1.5. Okay, so I can find the refractive index of glass using this information. Okay. Very easy to do. There is this third part. A convex lens has 20 centimeter focal length in air. Then what is its focal length in water? The refractive index of water with respect to air is 1.33 and the refractive index of glass with respect to air is 1.5. Okay. So you have a convex lens, assuming that you have made that with glass, that's what it is, right? Understandable from this problem. You have a convex lens, has a 20 centimeter focal length. So you have let's say I take a biconvex lens, and this convex lens has a focal length of 20 centimeters. Okay. This happens in air, and this is glass. This is glass, and this is air. Air, glass, air. So in this scenario, you get a focal length of 20 centimeters. Now the question is, take the same glass and put it in water. Okay, change the surrounding medium. Instead of air, you keep the surrounding medium as water. Then would you have the same focal length there? That's a question. Well, if you remember the lens maker's formula, it's given like this: 1 by V minus 1 by U is equal to N21 minus 1 into 1 by R1 minus 1 by R2. And this 1 by V minus 1 by U is also equal to 1 by F. Okay. So 1 by F is equal to, so 1 by F is equal to N21 minus 1 divided by 1 by R1 minus 1 by R2. Okay. So this is look at this. What is this N21? That is the refractive index of the second medium with respect to the first medium. So if the first medium changes, then this will also change. Instead of air, if the first medium is water, then you will have a different number for this. Okay? Why? Because you know N21 is simply N2 by N1. If it is N2 is the refractive index of glass with respect to vacuum. N1 is the refractive index of air with respect to vacuum. So this will remain 1.5 and this will be 1. So I get, in one case I get 1.5. But the other case, this refractive index of glass with respect to vacuum, and this will be refractive index of water with respect to vacuum. So you have a different number. So this will change. N21 will change depending on which medium you keep. This will change, right? So this will change. What about this? 1 by R1. That's the radius of the lens. Does it change? No, it won't change. Once you made the lens, whether you keep it in air or in water or in kerosene or in petrol, the radius of that lens will be the same. So that will remain. R2, that also will remain the same because you made the lens with those R1 and R2. So this won't change. So this will not change and this will not change. If you change the medium, this will change. And clearly this will change. Okay? So the focal length of a lens depends on the medium in which it is working. Okay? So I want you to understand that part. Okay? First, let me take the air glass case. So they say the focal length is 20 centimeters, right? So the first case, air glass. So medium 1 is air and medium 2 is glass. And one air to glass to air. In this case, the focal length is 20 centimeters. And what else is given? The refractive index N of glass with respect to vacuum or air, in this case air and vacuum will be the same, right? Glass with respect to vacuum is 1.5. The refractive index of air with respect to vacuum is 1, the same. So this is also equal to what? This is N2. N2 and this is N1. Right? This is 1, 2. Okay. So N21 in this case is equal to N2 by N1 equal to Ng by Na is equal to 1.5 by 1 to 1.5. Simply 1.5. I mean, I'm just explaining it, but it's very easy for you to. You don't even have to do all this. So refractive index of glass is 1.5, that is with respect to air too. Okay. Even though it is defined with respect to vacuum, it's the same with respect to air, 1.5. So you got that. Now you have some numbers, right? So let me take this equation. So it's going to be 1 by, what is this? F is 20 centimeters, I'm going to write as 0.2 meters, right? And that is equal to, this is 1.5 minus 1. And I have no idea what this is. I don't know R1 and I don't know R2. Okay, but what is this going to be? So 0.2, 1 by 0.2 will be 5. This is equal to 1.5 minus 1 will be 0.5 into 1 by R1 minus 1 by R2. Okay, so 1 by R1 minus 1 by R2 is equal to 5 divided by 0.5, 10. Okay, so this is very easy. And now I found the value of this term. 1 by R1 minus 1 by R2 is 10. I don't know the value of R1, I don't know the value of R2, but I know 1 by R1 minus 1 by R2 is 10. That's enough for me. Then what's the second case? The second case is water glass. Okay, medium 1 is water, because light travels from water into glass. Okay, so they want to define F here. So what is N21? So N21 is equal to N2 by N1. What is N2 here? N2 is glass, and then this is water. So this is Ng is 1.5 with respect to vacuum or air, and water is 1.33 with respect to air vacuum. So this is the number here. N21 is 1.5 by 1.33, which is not 1.5, it's less than that, right? You can see that clearly. Okay. So this term is going to be less than 0.5. So I can make use of this now. I know 1 by F I don't know, is equal to this number, 1.5 by 1.33 and minus 1. Okay, into what I'm going to do? 1 by R1 minus 1 by R2, the whole thing can be written as 10, very simply. So if I do this, then now I have everything, correct? So 1.33, 1.5 minus 1.33 will give me 0.17. 0.17 by 1.33 is what I will get into 10. So it will be 1.7 by 1.33, something like so. When you do this stuff, and you're going to have the F is, as per your book, it is going to be 78.2 centimeters. Okay, so when you do this, the focal length is going to be 78.2 centimeters. So the same lens for the same object. Okay, if you keep the object at one place, the same place, but just change the surrounding medium, then the image will be formed at a different place. Okay, So that's what it is. So the focal length for this setup, air glass setup, is 20 centimeters. Then for water glass setup is going to be 78.2 centimeters, so much bigger length. So the light bends slowly in this setup. The lens bends that light pretty slowly, you can say that in this case. Okay, there you had very good power. Now you see it's almost 80, so the power is reduced, to 1/4 of this. So the bending power, that also comes down. The F is more now, it's 80. So hope this is clear to you. The next item on our list is this combination of thin lenses in contact. If you take a single lens and if you keep an object on one side of it, and an image will be formed on the other side of the lens if you keep it at the right place. So what happens if I take two or more lenses and if you put them all together and if you keep the object? Where will the image be formed? And what would be the focal length of this combination? And how is this combined focal length, the focal length of the combined lens, all these individual lenses together? How is this focal length related to the individual focal length is what we will see now. We'll take two lenses. We take thin lenses. Why do we take thin lenses? That is because if you keep two thin lenses together and considering the distances involved, then you can ignore their thickness. So that's the reason you are using thin lenses. That's why it is called as the combination of thin lenses in contact. If they are very thick, then obviously your calculations could go a little wrong. But if they are thin lenses and if you're combining them together and the distances involved, the object distance and the image distance, if these distances are big in comparison to the thickness of all these things put together, then you can treat that lens as a single lens. That's the whole idea of it. Okay? So that is why we say this is a combination of thin lenses in contact. Okay, so let me take two. If I do it for two, then you can do it for any number. So first let me take this lens. This is lens 1, and let me keep in contact with another lens. In this case I am just taking thin lenses. So this is the axis. Okay. So let me say this is the center. Okay. This is the optical center. Okay. Very thin. So I can ignore this distance basically. That's what it means. Okay. So I keep the object here. So this is my object O. And what will happen now is, first, okay, this will maybe I'll put it slightly. Okay. So these two rays I'm taking to find the image. Okay. First, let's suppose that this lens was not there. Just the first lens was the only lens. And then what happens is that, like all the lines, all the rays that fall on this first lens will form an image there. And the position of the image can be found by using just two lines. Okay? So this line and this line would have gone straight. Okay? And this would have got refracted and maybe it would have come and hit here. Okay? So the image would have been formed here. Okay. So in that case, I can say that roughly this is my U and this is my, say I'll call this as V1 because this is the image formed by the first lens. Okay. But there is another lens. Okay, you brought the second lens. If this was not there, this is where the image would have been formed. Now we brought the second lens. Now what happens now is that this is going to converge the light further, and this is going to form an image somewhere here. Okay. So this is the actual image. So because of this combination, you have the object here and then you have the image here. If the second lens was not there, then the image would have been formed at I dashed. Because you brought the second lens, then it is formed here at this point. Okay. So, as we discussed before, I can say that for the second lens, this image has acted as the virtual object. The real object is here. But for the second lens, the ray which is coming from this lens is getting converged here. Okay. So, I will say that the image produced by the first lens is acting as the virtual object for the second lens. Okay. So clearly, as I said, like from the object, the rays must diverge. Here you see, this is object, the rays are converging. Okay. So that is the virtual object for the second lens. This is lens 1 and this is lens 2. Okay. Now, let me do, let's see, and also let me figure out this V. Okay, same, right? So this is going to be my V. So it's a final V. So this, I keep the object here and I have two lenses here, then this is where my final image is formed. So this is U and this is V. Okay. So this is for this combination. Okay. Now, for the first lens, let me do the lens formula. So that is going to be 1 by, for the first lens, what is its V? Its V is V1 now. 1 by V1 minus 1 by U is equal to 1 by F1. But F1 is the focal length of the first lens. So that's clear. Okay. And for the second lens, which is the V, this is the V, right? This is the V. Which is U, this is the U. So this is the U for the second lens, and this is the V for the second, because it's taking object from there and then forms the image here. So for the second lens, this is for the first lens. For the second lens, V is 1 by V only now, this V. Then minus 1 by, now what is this U? This U is actually this V1, right? So the second lens, V1 is U, so V1. And that must be equal to 1 by F2. So this is equation 1 and this is equation 2. Okay. And for the combination, I am going to treat these two as single lens now. So if I treat them as single lens, this is where I kept my object and this is where I get my image. So the focal length of this combination can be given by this expression, right? So what is the combinations to be? This. So 1 by V minus, what's the combination to U? This. U, 1 by U equals 1 by the focal length of the combination. Okay, okay, so this is my equation 3. Okay, notice that I can get to 3 from 1 and 2. If I add 1 and 2, I'll get this. If I add 1 and 2, I'll get, see, 1 by V I'll get simply, and then minus 1 by V1, then plus 1 by V1 minus 1 by U, which is equal to, first one is 1 by F2 plus 1 by F1, or you can say 1 by F1 plus 1 by F2. Okay, so this and this cancels. So I get 1 by V is 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. So this is my equation 4. Okay. So this is equation 3 and this is equation 4. So since 3 is equal to 4, what do you get? 1 by F is equal to 1 by F1 plus 1 by F2. Okay, so this is what I get. So the effective focal length of this combination can be found using this formula. So the other way to write this would be from the power formula. So this is going to be equal to 1 by F1 is the power of the first lens and 1 by F2 is the power of the second lens. Okay? And if I keep one more, just by induction, I can say that this 1 by F is equal to 1 by F1 plus 1 by F2 if I add 1 by F3 and so on. If I keep n number of thin lenses together, then the combined focal length can be obtained from this expression. Next thing here, this is the power of the first one, power of the second one, this would be the power of the combination. So the power of the combination can be written as P is equal to P1 plus P2 for this case. And for the most general case, then I can say that power is equal to P1 plus P2. In the case of mirrors, we discussed the magnification. We said the magnification is equal to the image size divided by the object size. So this is how we define it. And if you take a linear, obviously if you take a point object, there would not be any magnification. The reason is that the size will not change. Point is a point source or point object, has no dimensions, so that's not going to get bigger or smaller on the other side. A point is dimensionless, so doesn't make any sense to define magnification for a point object. But if you take a linear object, and clearly the length can change. If I have an arrow, then that arrow can become smaller or bigger in the image. So what is the length of the arrow and divided by the length of the object? That would give me the magnification. Secondly, you can do the magnification for an aerial object too. So you have one area of the object, and then you get an image of the object, and the image could be bigger or smaller than the object. So you will get an aerial magnification. So this is maybe in say a certain meter square, and the object could be in some meter square, and the image could be in a different meter squares. Then the image size divided by the object size will give you the aerial magnification. Okay. So right now we will be dealing only with the linear magnification. We will be dealing with only one-dimensional objects. So whenever we say this magnification, then it is image size by object size, which means an image length divided by the object length. So that is how we do it. Okay. So in the case of a mirror, for example, if you take a concave mirror, then if I have something like this is the focal length, and let's say this is the center, and then suppose if I have an object here, so this is A and this is B. So see, you can go ahead and then can do this. Also, parallel ray I can take, and then that can come like this. Let's say this is going to make an arrow like this. So this could be this is my B dash and this is my A dash. So this could be the image. So I say this length divided by this length. So that's the magnification. So when you do magnification like this, you see that these are similar triangles. Let's say this is 4. If we take triangle APB and triangle B dash A dash P, B dash A dash P, they are similar triangles. Right? So, which means that what's the magnification? Magnification is actually M is equal to image is A dash to B dash, object is AB, is what it is. And how do I find it here? Okay, if I take these triangles, then A dash to B dash divided by AB is equal to PP dash divided by PB, because it's a similar triangle. So that gives me PB dash divided by PB. Okay. So then this results in, what is PB dash? PB dash is nothing but V, right? V. And then PB is actually U. Okay. So this is a negative quantity and this is also a negative quantity, V and U. So negative and negative will get positive value, but you don't want that to happen, okay? Because the image is inverted now. To get the information that this is inverted, and you are going to have a negative sign here. So this is, finally this became your magnification. M is equal to minus V by U. This was your magnification for a mirror. So then for a lens, this would be the same. Okay, if I have a convex lens, for example, something similar, right? So this is the axis, then I have a linear object here, then this is the focal length there. So if we draw a straight line, then that will go through it. Okay, and then if we take another line and go through this, and you see this is going to mark, this is where the image is going to form. So this is A and this is B, and this will be B dash and this will be A dash. So you know this. Okay, so again, this is going to be O, optical center, right? So look at this. In this case, this triangle ABO, this triangle, and OB dash A dash, and triangle OB dash A dash are similar. You can get this idea. Let me just draw that in a different color now. So this triangle and this triangle are similar. If they are similar, then magnification, as usual, is image size by object size. The image size is A dash to B dash divided by AB, and that is going to be equal to A dash to B dash into OB dash divided by OB. But what is OB dash? OB dash is V. What is OB? That is U. Okay. But notice here, I have got the sign already taken care of. Look at this. So my V is positive and my U is negative. So V by U will be a negative number. Notice here, it is already inverted. An inverted image will have a negative number, right? So I am going to leave it like that. I am not going to make the adjustments I made here. Here this was different. This was negative, this was also negative. So it gave me a positive number. So I had to introduce a negative sign there. But here I actually know it's inverted, the image is inverted. But V is positive and U is negative. So V by U itself will give me a negative number. So the inverted nature of the image is already taken care of in this equation. So for a lens, the magnification formula is equal to V by U. For a mirror, the magnification formula is M is equal to minus V by U. Because in both cases, V and U will be having signs. When you measure V, it will have a sign. When you measure U, that number also will have a sign. So you are going to put only numbers with signs for V and U. And when you do that, this will have this expression is for the mirror and this expression is for the lens. Okay? So this is what is happening. And we've just seen that in the case of the combination of thin lenses in contact, so like this, when you have lenses like this, when you have thin lenses in contact, and when you have an object here, and then you are going to have an image somewhere here. Okay, for this, we said 1 by f, the focal length of the combination was equal to 1 by f1 plus 1 by f2 and so on, and which means that p is equal to p1 plus p2 and so on. Okay, we did that. And what would be the magnification for this? The magnification, it turns out that the magnification of the combination is equal to magnification of the first one multiplied by the magnification of the second one, m3 and so on. So we keep multiplying the magnification, and that would be the magnification of the combination. So I want you to remember this too. I have not proved it, I have not derived anything for it, but take it from me that if you try to do something like this, then you will end up with this kind of an equation. Okay? So hope this is clear to you. Okay, now let's do an example problem. This problem is 9.9. Find the position of the image formed by the lens combination given in the figure. So this is the picture. So this is the axis of all those lenses. There is a lens here. So biconvex lens, and this has a focal length of 10 centimeters. 10 centimeters. And there is a plano-concave lens. Okay. So that's kept like this, and the distance between those two is 5 centimeters. And this focal length is minus 10 centimeters. Okay, clearly it's a concave lens, so the focal length has to be negative. We know that, we've seen that already. And then there is another lens, biconvex lens, that is 10 centimeters from this lens. Okay, and the object is kept 30 centimeters to the left of this lens. So the object is kept here. Object is kept here, and that distance is actually 30 centimeters. So they want you to find the distance at which the image will be formed. So I call it as AB. This is AB. So image will be formed. See, just because we have just discussed combination of thin lenses in contact, you cannot use the formula 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 here. You can't use it here. The reason is, you can see that these lenses are not in contact. If these lenses are not in contact, you cannot use that formula. Even though we did that formula, 1 by f is equal to 1 by f1 plus 1 by f2, you can't use that formula because they are not in contact. So you have to do these things separately. Okay? First, let me take the first lens. So the focal length is given for the first lens, lens 1. Okay? The focal length is 10 centimeters. Okay? And then this distance u is 30 centimeters. So then the object is here. So the light is traveling in this direction. So u must be minus 30. Minus 30 centimeters. You don't know v. V is what you need to find. Okay? So I can use the formula now, right? So what is the formula? 1 by v minus 1 by u is equal to 1 by f. So 1 by v I have no idea. Minus 1 by u is minus 30. And that must be equal to 1 by f is positive because there is convex lens, so 1 by 10. So then 1 by V is equal to, now got plus 30, right? So I get 1 by 10, this is 1 by plus 30, then it goes there minus 1 by 30. So this may result in 30 being the LCM, and this becomes 3 minus 1. So 1 by V is equal to, I'll say this. So this is also equal to 2 by 30, that is 1 by 15. So V in this case is equal to 15 centimeters. So what will happen is that this will form an image. This will form an image 15 centimeters. Okay, so maybe somewhere here, right? So 5 plus 10, okay, maybe somewhere here it's going to form an image. I don't know, maybe this. Okay, so this at 10 is somewhere here, something like this. Okay, if these two lenses were not there, this would have formed the image here. Okay, somewhere there. Doesn't matter. Okay. But what happened? That image is not going to be formed there because you have brought in another lens here. So that's going to intercept these rays, right? So you're going to converge or diverge those rays from this position. They are not going to converge here because you are using a diverging lens, concave lens. So the rays will diverge. Okay, they won't converge there. Anyway, we'll see what happens there. Now lens 2. Lens 2. The focal length of that lens is minus 10 centimeters. Now, what is U? What is U for that lens? Well, the image for this is going to be formed 15 centimeters from this lens. So this is going to be 15. Yes, so 15 centimeters. That's what I calculated from that lens. But from this lens, which is kept here, 5 centimeters after that lens, then the U is only 10 centimeters now. So U for this is only 10 centimeters. Okay, so now 10 centimeters. Okay, now is the question. But is this a real object or a virtual object? This is a virtual object for this. So you see, this is what it is going to use as the object, where the lines are converging. Actual object is here. It's going to be a virtual object here. One. Okay. And what is U value? For this, the light ray is traveling in this direction. So U is also here. The virtual object is also in that direction. So the measurement of U is a positive number for this. Notice. For this, the measurement of U was a negative number for a real object. But here, you see, if you consider this, it's going to be a positive number. It's the other way around. Okay? So this is going to be a positive number for it. This is where the virtual object is for this lens. So that is positive number. Okay. Now I can find V. That is 1 by V minus 1 by U is equal to 1 by F. So 1 by V minus 1 by 10 is equal to 1 by minus 10. F is negative number here. So if you bring it there, you bring it to the other side, I can cancel this, right? So 1 by V will become 0. Minus 1 by 10 plus 1 by 10 will become 0 now. So if 1 by V is equal to 0, then V must be equal to infinity. Okay? So this is like, this will form an image at infinity. This lens will form an image at plus infinity. Okay, this happened to form it. That is the case. If this is infinity, then where will that form the image? Now lens 3. This image. Where will this form? Okay, this is like, if it will form the image at infinity, then what will this do? I'll use a different color now. This will take that and it will form, this will be a inside parallel lines. Okay, for all the other lines will go parallel from here. So only then the image will be formed at infinity, right? So this is what you get here. So now you get parallel lines there. So clearly, we will see what's going to happen. Okay. Next, lens 3. So what is its f now? For lens 3, f is equal to, how much is it? It's 30 centimeters. This f is equal to plus 30 centimeters. So convex lens, so that's going to be plus 30 centimeters. So f is equal to plus 30 centimeters. Okay, just like plus 10, you get plus 30 centimeters. Yeah, and remove this 30 centimeters. And its u is equal to infinity. Because it's going to form the image. It's going to send parallel rays. Only then can the image be formed at infinity for this lens. So for this, u as measured, it is at infinity. Okay, its virtual object is there at infinity. Okay, and what is v? V is what we need to find. So 1 by v minus 1 by u is equal to 1 by f. So 1 by v, I don't know, minus 1 by u is infinity, so that becomes 0 anyway. So that is going to be equal to 1 by, what is f? F is 30. Okay, so this will become 0. So 1 by v is equal to 1 by 30. So v is equal to 30 centimeter. So v will be formed here on this side. Okay, the parallel, all the parallel lines will form an image here, right? So it's going to be 30 centimeters. So this is f. Okay, so this will be 30 centimeters. So object is at infinity, then the image will be at 30 centimeters. Parallel lines will converge there. Okay. So V is equal to 30 centimeters. So the image will be formed 30 centimeters from the third lens. That's the answer. So this is how we do this problem. But the point to remember is, don't try to use a thin lens formula which you just derived. That is for the combination of thin lenses which are in contact, which touch each other. But here they are not touching each other. They are different lenses. One lens tries to form an image and another lens intercepts those rays and then tries to form its own image. And then the third lens intercepts those lines and then tries to form its own image. So when you keep an object here at 30 centimeters, then even if you keep lenses like this, and the image will be formed 30 centimeters from the third lens.